We start off this video with a seemingly unmotivated definition. Given a vector B in Rm and a subspace V of Rm, we define the orthogonal projection of B onto V to be the vector B hat in V that is closest to B. So on the face of it, this seems unrelated. So on the one hand, we're defining an object to be what's called an orthogonal projection, but nowhere in the definition is the word orthogonal present. So since this seems like a hard object to pin down, let's think about a really simple example. Let's take the vector V, whose coordinates are 2 and 1, living in R2. This vector spans the subspace L, which is defined by the equation y is equal to x over 2. So as you imagine, this is just a line with slope 1/2 through the origin. So we're going to take a vector b, and we're going to let the coordinates of this vector be x0 and y0. Our goal is to find the vector b hat, which lives in L, so is of course t times v for some t, that is the closest vector on that line to b. If b lies on the line, then we can simply take b hat to be b. So we might as well assume that b does not lie on the line L. So let's start out by drawing a picture. So here we have R2 with our standard basis and standard coordinates. We start off by drawing the line L and a vector b. So first, we're going to take the line L prime, which is perpendicular to L, and passes through the point at the tip of B. So if we choose a vector, let's call it S times V, that points from the origin to the intersection of these two lines, L and L prime, then we can see that the vector, which points from the intersection of L and L prime to the tip of B, will be the vector B minus SV. If we choose any other vector RV on the line, then we can see that the vector B minus RV will form a right triangle, where here RV minus SV is the base of our triangle. The Pythagorean theorem tells us the length of the vector B minus RV squared must be equal to the length of RV minus SV squared plus the length of B minus SV squared. So remember, we chose SV so that the vector B minus SV is perpendicular to the line L. So our inequality tells us that the distance from B to RV is at least as large as the distance from B to SV. So this vector SV is the one that is closest to B and on L. That is, this vector SV must be B hat. So of course, if we want to identify what B hat actually is, we'll need to use this defining property that B minus SV is perpendicular to the line L. We'll distribute the V across to get V dot B minus S times V dot V is equal to V dot B minus S times the norm of V squared. We can add S times the norm of V squared across. And then, of course, to solve for S, we simply divide by the non-zero scalar the norm of V squared. which is simply 2 times x naught plus y naught divided by 2 squared plus 1 squared, which is 2x naught plus y naught, all divided by 5. So to find b hat in particular, we simply take the original vector v, which was 2, 1, and we multiply it by this scalar. So for example, if our original vector b had coordinates 4 and 2, b hat is 1/5, 4 times 4 plus 2 times 2, 2 times 4 plus 2 is a fifth, 2010 is 4, 2 itself, which of course is exactly what we would expect because this vector lies on the line y equals 1/2 x. If we were to flip these coordinates, so our x coordinate becomes 2 and our y coordinate becomes 4, then b hat is 1/5, 4 times 2 plus 2 times 4, and 2 times 2 plus 4, which is 1/5 of 16 and 8. So we see that when our vector b does not lie on the line y equals 1/2 x, we do in fact get a different vector. So before we move on to talk about this in more generality, we have a couple of quick remarks. The first remark is for those of you who may or may not have enjoyed watching a geometric argument. So of course, if you're wondering whether you can do this a different way, the answer is yes, if you're willing to do a little bit of calculus. So instead of thinking about vectors, we'll think about points. So rather than thinking about the vector b, we'll think about the point x naught, y naught. And we'll think about a second point. It will, of course, have coordinates x, 1/2 x. To measure the distance between these 2 points, we'll get a function of a single variable, which is the square root of the difference of the x coordinates squared plus the difference of the y coordinates squared. We can square in order to get rid of the square root. If we want to minimize the distance between the line L and the point x naught, y naught, we can take the derivative using the chain rule. This gives us 2dd prime is twice x minus x naught plus 1/2 x minus y naught. Divide both sides by 2 and rearrange gives us 5/4 x minus x naught minus 1/2 y naught. So we see that the derivative of the distance function is 0 if and only if 5/4 x is equal to x naught plus 1/2 y naught, which is of course equivalent to saying that x is 4x naught plus 2y naught over 5. It's an easy exercise to see that the derivative will be positive to the left of this point and negative to the right of this point. So this is in fact a minimum of the distance function. So the y-coordinate of the point which lies on the line is the one that is 1/2 this x value. And of course, if you identify the vector b hat with the one that points from the origin to this point, then you can see that these two solutions absolutely agree. Our second remark is intended to explain why we might call this vector b hat projection. If L were the span of the vector E1, then we can identify this line L with the x-axis. If we're given a vector b and we want to find the approximation b hat, then we just need to solve the equation 0 is equal to b minus t times e1 dotted with the vector e1. So the solution is t must equal x naught. So of course the vector b hat, which is the orthogonal projection of b, is really the projection of b onto the x-axis. Similarly, if we had chosen L to be the span of the vector E2, then instead of projecting onto the x-axis, we would get the projection onto the y-axis. So of course, this does actually mean projection in the way that one normally means the word projection. In the next video, we'll talk about how to do this in a little bit more generality.